Today we're going to talk about polar coordinates and path coordinates. At some point today or Tuesday, I was going to try to tell you a little bit about the whole flow of the course. I realized that the table of contents is a little hard for some of you to understand what the logical progression is. And there is one, and it's a little subtle. So would you rather have that today or rather have that Tuesday? Anybody care? Today? Tuesday? Nobody cares. Well, I'll see how the time goes. Okay, here's the big idea. It's the Laurie-Anderson equation. It's that A equals A. Now, it looks like a stupid equation, but once you get it, you'll suddenly say, oh, now I see what he means. A equals A. I will say it, and I know it takes bit by bit. It will get into each of your heads, but at each point in time, you don't quite get what I'm saying, even though all the words are there. But I'm going to say it again. We have this concept, acceleration equals acceleration. What we mean by that is a vector is a vector. We're going to represent a vector, say, from my shoulder to the tip of my finger, and that vector is that vector. You can think of it as an arrow in space. How you represent it is your choice. There are lots of ways to represent that vector. So it's also true of position vector equals position vector, r equals r, v equals v, any x equals x. But the most important vector for us that's hard to calculate in this class is acceleration. Say this is an acceleration vector. You could represent it with x and y coordinates, or you could draw some crooked coordinates, say parallel and perpendicular to some slope, and represent it in terms of those coordinates. It's still the same acceleration vector. Or you could use polar coordinates or path coordinates or some moving frame coordinates, which we haven't discussed yet. So let me just draw the picture here. Let's say there's some origin, and associated with that origin, we could have various reference frames. We could have, for example, I and j, or we could have some crooked frame, I prime and j prime. And we can look at some particle which is out here someplace, and this is the particle of interest, and it's traveling on some path like this, and we can pay attention to coordinates that are associated with this particle, say e sub r and e sub theta. And there's actually two more natural basis vectors, or one more natural coordinate system which we haven't discussed yet, but I'm going to discuss today. And now, according to Murphy's law of drawing, two lines will end up parallel that you do not intend to be parallel. So this line is not intended to be vertical. So I just gave a demonstration of Murphy's law of drawing. I want that line to be not parallel to the y-axis or to anything else. And associated with this path is a tangent line. And there's a vector associated with that, which we can call ET. And there's a vector in this perpendicular direction, which we can call En. So when we write A equals A, what we mean is that the acceleration, we can represent it as x double dot I plus y double dot j, but that same acceleration vector we can write as x double dot prime I prime plus y double dot prime j prime, where implicitly we have here an x direction and a y direction, and an x prime and y prime, which I won't draw here. Okay, so if I just go this far, do people have trouble, does anybody have trouble saying that this is equal to this, even though this number is not equal to this number? Does that bother anybody, or does anybody want me to discuss that in any way, shape, or form? Yes? What do we mean by acceleration, by the way? Always when we write acceleration, we mean the acceleration relative to some fixed frame. So that means the time derivative of this thing measured relative to some fixed frame. This is the fancy notation. Is that what you're talking about, what we mean by acceleration? Okay, so in every case here, we mean this acceleration. We mean that here, and we mean that here. So this vector is equal to this vector, even though this number is not equal to this number. Clear? Yes?
Is there a reason why you set up En et again instead of just continuing with e theta and er?
Well, they're different things. So ER is defined to be R divided by the magnitude of R. And ET, and I'm going to show this to you, but I'll just complete the picture now, is defined to be velocity divided by the magnitude of the velocity. And these directions are not the same as each other. Two different directions. So we have 4 different coordinate systems on this one picture. And associated with each coordinate system, we have a different representation of the acceleration. So in polar coordinates, and I'm going to derive this for you, and I think I derived it for you before, but I'll do it again. In polar coordinates, the formula for acceleration looks like this. And then finally, in this funny, what are called path coordinates, the acceleration looks like this. And I'll show this to you also, but I'm just writing it here for completeness. And in this definition is this quantity rho, which is not on the picture, which I'll discuss later in class. But in case you're curious, it's the radius of curvature of that arc at that point in space. But the key thing here is that A equals A equals A equals A. And you can use any of these in any equation that involves acceleration, or you use acceleration in F equals ma, or you use the acceleration in angular momentum balance. Okay, so I want to do a problem, and in the middle of doing this problem, I'm going to derive this formula. Did I derive this whole formula for you in lecture, or just half of it? Do you guys recall? What? I derived the whole thing already in lecture. Okay, so I'm going to not derive this again. Does anybody have feel a need to see that derivation again, or can you go back and look at the video, read the book, look on Wikipedia, whatever? Who wants to see it again? Okay. For you, I'll do it. Everybody else, just mind your own. No, never mind. Okay, so I want to do an example. This example I'll call the new gun, which is a little machine, and I brought a copy of this machine here. And the way this machine works is I'm going to have a motor, and this motor is going to be connected to a rod. And for keeping this problem simple, I'll say G equals 0, and I'll say mu is equal to 0, which doesn't mean gravity is 0, and it doesn't mean friction is 0. It means we're neglecting them in this problem. We're approximating them as 0. And this motor is going to turn at a constant rate. So I'm going to say omega equals a constant, which is given. And on this rod, we're going to put this bead, which has a mass m. At this instant in time, it's going to be out here a distance r, and it's going to make an angle theta here, which is going to increase linearly in time because omega is a constant. And here we say there's no friction. I said that already. And this thing is going to be flying along. So how do we set this up? We take here's a motor. Literally it is. Muscles are motors. I'm going to turn this thing like this, and I'm going to put a bead on here, and I'm going to make it frictionless. Dan. I'm not going to make it frictionless. Does anybody have any lubricant of any? You actually have grease? Can I have one little drop of it? Just squeeze out a drop into my paper. I got a pocket knife, but I guess you win. Just a little. There you go. Okay, so then I put this here like this, and I'm going to flick my wrist around, and this is going to fly across the room. Okay? Now actually it's rather dramatic what happens, and I hope I don't cause damage. I want to find this afterwards so I could maybe do this more than one time. Are you ready? Okay, so it goes kind of fast. Does anybody see where the thing... Okay, you want to see it again? Okay, so I hold my wrist like this. Okay, so this thing is flying out like this, and we're going to catch this at some instant in time and look at it at some instant in time. So here it is at some instant in time in this process. And at this instant in time, we could look at the acceleration, and we could imagine the acceleration was in this direction, or in this direction, or in this direction, or maybe it depends. This direction is not meant to be vertical, it's meant to be something sort of like that. And we could call this A, B, or C, and we could ask the question, is the acceleration equal to A, B, C, none of above, or E cannot be determined? So the question is when you catch this thing in slow motion, you've got your slow motion camera on, you got this thing, but before it left the rod, the motor is turning, we catch it right in the situation. Right at that point in time, we're neglecting gravity. Is the acceleration in that direction, some crooked direction, or orthogonal to the rod? And you get to vote. And the vote is not running yet. Now the vote is running. You can talk to each other. 30 seconds to talk about it. Okay, 20 seconds left. Okay, does anybody want to advocate for one of these positions or another? You can keep voting if you want to. Yes?
I'll advocate for C because there's no force along the line, along the rod.
Okay. See how persuasive you are. Well, that sounded good. Anybody want to advocate for B? Whoa. Should run for office, man. Anybody want to advocate for B? The power of words. Well, this thing is flying out. And it clearly has a radial acceleration because the radius is increasing in time. It leaves here with one radius. It ends up with a different radius. Certainly the radius is increasing radically in time, so it seems like it might make you want to rethink that. And then at the very end, it's shooting right off the end. So it must be going straight radially, so maybe it's going radially the whole time. Okay, stop. Okay, so how are we going to do this problem? Well, like all problems in mechanics, it involves the laws of mechanics, geometry calculations, and material properties. Often in this class, the material properties aspects are kind of simple because they're extreme. Like mu equals 0 as a material property goes in a subtle way. Or the objects are rigid. Or, well, gravity is equal to 0. But we have to put, somehow or other, all those three ingredients go into every mechanics problem. Here we have this situation. The rod is like this. Here we have this mass like so. And we draw the free body diagram with a force in this direction. There could be a force of gravity, but we said gravity is negligible. Why is gravity negligible? Because I flicked it so hard that we think the other forces are so big that gravity has a small effect. If I flicked it slowly, obviously gravity would not be negligible. So we're assuming this is a right angle here. We don't draw a friction force here because we said there's no friction along the line because I put grease there, which doesn't have 0 friction, but we said it's small enough so we can neglect it to do this calculation. I call this thing n, or I could take this whole collection of things here and I could draw this arrow again and I could call this n e theta, which means that I'm associating with this problem at this instant in time an er and an e theta. So that means out here at this instant in time, there's an r and there's a theta. And I try to draw these r and theta, so even though they have arrowheads, they're far enough removed from this and drawn enough differently so that there's no confusion about which is forces on the free body diagram and which are little dimension lines. And I draw the force on the outside, so you see this is acting on this thing. Really, I'd like to draw it in there, but it gets confusing. Any problems with this free body diagram? Or questions about this free body diagram? Okay, now we get to linear momentum balance, and we write that the sum of the forces on this thing is equal to the rate of change of linear momentum, which is the mass times the acceleration. If we're just modeling this as a particle, we're not worrying about the rotational dynamics of the little thing there. Then we have over here for this force is n times e theta. And then over here for the acceleration, well, this thing is moving on some path. And we could write the acceleration in this path coordinates, and this er, e theta coordinates, and x and y coordinates. It happens that nearby there's a slope that a car is going down, and we could have had an I prime or and a j prime coordinate system that just happened to be in the problem for other purposes. We can write the acceleration any way we want. There's not a right way to do it. There's just a way that makes the algebra easier for us. So we could choose to use Cartesian coordinates here for the acceleration. It's just we'd be in a world of mess. Now, if you're good at dynamics, you should try this problem in Cartesian coordinates and see that you can get in and climb out again. It's just much harder than using polar coordinates. This is a setup for polar coordinates. Why is it a setup for polar coordinates? Is because we're told what theta is as a function of time. We've been given a kinematic constraint, and we can eliminate that constraint implicitly by just representing things with r and theta. If we represented things with x and y, we'd have to add that description that it's always on this radial line in x and y coordinates. In polar coordinates, it's very simple. We just say theta is given by this equation. So, of course, this is a problem that's set up for polar coordinates. It's like the best problem for polar coordinates. So we write the acceleration in polar coordinates for this problem. Go ahead, write it down while I find the chalk. What do you write down? You just copy the formula, which is on the board over there. It's mass times something er plus something e theta. What's the something? It's r double dot minus r theta dot squared. It's r theta double dot plus 2r dot theta dot. Now, this is, if you just look at it and you're not used to it, it's a crazy looking formula. Right? It's got Greek letters in it, at least one. It's got double dots. It's got 2 in it. It's got minus signs and plus signs. It's got hats. It just looks like a crazy formula. You would like, if you can, to make this not a list of symbols that you memorize, but something where you understand each term. How can you understand each term? Is you can do the derivation, watch it very carefully, or you can try to think physically about each term. How can you do that? Is try to invent a situation where all of the terms are 0 except for 1. And then you can understand that term. And by far the hardest term to understand in that way is this one. And well, when I first learned this formula, I remember I went and just stood at a blackboard and I spent 2 or 3 hours just drawing pictures and making sense out of this term. And if you want to learn the material, I recommend you do the same thing. Okay, so we have this equation. And now the algebra of polar coordinates is just too nice to us. In other words, this problem, which just looks hard, it just collapses. Why it collapses so beautifully is sort of hard to understand, but it just collapses the following way, which is, if we don't care what this thing is, and we're trying to solve equations, the simplest thing to do is to just try to get rid of this term. Well, how can we get rid of this term? Is we can take the dot product of this equation, both sides, with a vector which is perpendicular to this. So once you believe this crazy equation and can work with it, then you get this beautiful answer all in one step, which is we take the dot product of this with ER, and it tells us that 0 is equal to, now the m goes away, all of this stuff goes away, and we get r double dot minus r theta dot squared. Well, remember theta dot was a constant, so this is just r double dot is equal to omega squared r, and this was a constant. So now we've got our differential equation of motion. Just beautifully, simply like that. What about the answer to this question over here? Can you spend 30 seconds talking to each other about this question? Using the equations that are on the blackboard now. Okay, can you guys get twice as loud, please? Okay, at the count of 3, everybody say F equals MA. 1, 2, 3.
F equals MA.
Now keep using those voices and talk to the person next to you. Okay, so question is, do you believe this equation? If you believe this equation, your vote should be different, most of you. This says this is the acceleration. The acceleration is the sum of two vectors, one in the r direction, one in the theta direction. How big are these two components if you use this equation? Right, you all have some intuition for mechanics here, mechanical engineers and so on, but there are these beautiful formulas, and the formulas are right too. And in fact, if you're good at the formulas, they're more right than your intuition. And you want to get your intuition and the formulas in line, not just ignore your intuition and do algebra blindly and have factors of 2 and minus signs, nor do you want to use your intuition and just write answers that are blatantly in contradiction to the formulas you're supposed to trust.
So what you're thinking could or could not be right.
So look at that formula. What does that say about the size of the part of that acceleration vector that's in the ER direction and the E theta direction? Talk a little bit. I'd like these people to especially talk. I don't mean go with the herd. I mean talk and understand. Okay, so here's how it goes. Does anybody have doubts about this equation? Is there something wrong here? Did I make an algebra mistake? Do you think it's not right? Is there something suspicious about it? It doesn't belong here. There's some hidden assumptions. Does anybody have any problems with this equation? Or maybe insecurities that I could help them with? You have problems in your childhood and you don't quite trust the Greek letters or something. Is there something I could help somebody with? Yes? You're trying to figure out what this term is about. Why is this term here? So the question is can you figure out why there's an acceleration associated with this? You can derive it, you don't understand it physically. So I will try to explain that term to you physically. Are you ready? Okay, so this formula supposedly applies for every r and every theta. Let's try to find a situation where the other three terms are 0. So such a situation would be, for example, if theta dot is a constant and this term is 0, and if r dot is a constant, so this term is 0, and if r is equal to 0, so this term is 0. So what would that be? It would be this thing is spinning at a constant rate, and this bead is moving at a constant rate along here, and we're looking at it just at the instant when it passes through 0. And we'd like to figure out what the acceleration is. Well, this thing is spinning in circles. This rod is, and this is coming in on this thing, and it's going out on this thing. So if all you do is watch this bead, even though r dot is constant and theta dot is constant, this bead is going on a curved path at some non-zero speed. So it has to have some acceleration because the velocity vector is not constant. Certainly if it's going faster, it has a bigger acceleration if r dot is bigger, and if this is spinning faster, it has a bigger acceleration. So that's why there is some acceleration even when r dot is constant. There's no r double dot, and even when theta dot is constant. Now why the factor of 2? Okay, now why the factor of 2 is there's two things which are happening. Here it is here, and then it's going to pass to here. Or we can start from 0 and go to here. In the process of going from 0 to here, one thing that happens is it goes out to here, and at this point, if you freeze it, it's going in circles. So it's picking up a circular motion, which is proportional to the size of the circle in theta dot. And the speed associated with that circular motion is increasing the bigger the radius, so that's r dot theta. On the other hand, it's got some velocity in this direction, and the direction of that velocity is changing. So the radial velocity part is changing its direction, and that also gives you an r theta dot. And those are the two terms you picked up when you differentiated the velocity formula. Okay, does that address your question? Okay, so I just gave you back the 2 hours that I invested when I was a sophomore. Okay, anything else suspicious about this? Okay, so now you trust this formula, weird as it is. And here we have force is mass times acceleration. F equals ma. It's the biggest equation in this class. If you believe this, and you believe this free body diagram, this says that there's no force in the radial direction. So if we take the dot product of both sides with ER, we get this R double dot equation, but we could do the opposite. Sorry. It says that this term is equal to 0. This is the radial component of the acceleration. So it says this vector, when we dot it with ER, this vector, whatever it is, when we dot it with a vector in that direction, gives 0. Does this vector dotted with ER give 0? No. Does this vector dotted with ER give 0? What's left is just that one. So even though all the excitement is in the radius changing in time, the actual radial acceleration is 0. So this thing is moving on this funny path. So let's draw this thing at some point in time. Here's the rod at some point in time. Here's where this thing started like this. It's going to end up flying away like this. It starts out, if we start it, it starts out going up, but then it goes over to this exponential spiral. And this angle here, I shouldn't have drawn it quite like that. It actually crosses, after a while, it starts crossing at 45 degrees. So here's the path of this thing. Here it is at some instant in time. We have the r vector. This is the position vector. We have the velocity vector. The velocity is always tangent to the path. And then we have the acceleration vector. And my claim is that the acceleration vector has to be in exactly this direction. Now that direction is orthogonal to the radial direction. How can it be that the radius increases when the acceleration is in that direction? That's the intuitive conflict, right, that you have. How can it be that it's accelerating that way, but this radius is increasing? Well, because the direction of this radius is changing. If all it did was go in a straight line in that direction, the radius would increase. So it always has an acceleration in this direction, which is a part speeding up and a part orthogonal, and the radius is increasing in time. Okay, now how does it increase in time? We can do the calculation. This is a constant coefficient, second order, linear ODE. And what's the differential equation? We have r double dot equals omega squared r. Did I put a minus sign there by accident? No, I didn't. And we have the initial condition that r of 0 is equal to 0. And we can assume that we started from rest. So we started at 0 radial velocity. So we have a differential equation and initial conditions. And this is one of the ones you should just sort of know the solution to. Can anybody just tell me the solution, complete solution, all the constants right and everything from the beginning? By the way, I didn't mean 0 here. I meant R0. Okay, well it's like the first order exponential growth where the rate of change is proportional to size. Here the acceleration is proportional to size. With that acceleration, it's a second order equation, so there's two solutions. We get exponential growth and exponential decay, just like the inverted pendulum, which I discussed for some time in class. It's got exponential growth away from the equilibrium, but if you launch it just right, you can get exponential decay up to the equilibrium. And the general solution is the sum of those two. After a while, the exponential growth dominates, but if we want the full solution, we have both terms. If you have exponential growth and exponential decay together, there's special functions which work out nice for differential equations. You take the sum of the two and divide it by 2 and call that a new function, which is called hyperbolic cosine. You take the difference, divide it by 2, it's hyperbolic sine. Hyperbolic sine is nice because it's 0 at time equals 0. And if we go through and set all the constants right for this, we get that r is equal to R0 cosh of omega t. Or another way to write that is R0 times e to the omega t plus e to the minus omega t divided by 2. What does that give us for this thing as it shoots along if we put in, say, R0 equals 0.5 meters and we put omega equals, say, 5 radians per second, and we put in theta max is equal to, say, pi, then this gives us that the final R dot is about 60 miles an hour, or the final V is something like 85 miles per hour. Now, is that what I just did here in lecture? No, I didn't go all the way to pi. If I'd gone all the way to pi, it would have shot into the ground. Also, you can calculate what's the radius by the time you go an angle of pi, and the radius is something like 11 meters, and I didn't get there. So what I did was something less than that, but it's this big amplification. As this goes around, there's this exponential increase in speed. Actually, there's some interesting things here. We can rewrite the solution that the R is equal to R0 times hyperbolic cosine of theta, because omega t is theta. And this is approximately equal to, when theta gets large, R0 times e to the theta divided by 2. So it's a simple exponential growth after we get rid of the initial exponentially decaying term. If we want to know the vectors as a function of time, we now know r as a function of time. So if we want to know the r vector as a function of time, we can write r of t equals r e theta. And let's say we wanted to plot this with x and y coordinates. We could say e theta is cosine theta I plus sine theta j. But wherever we see theta, we can put omega t. And wherever we see r, we can plug in what we have for r, which is that r is equal to r0 cosh of omega t. So we can get r of t like this, and we can write v of t, if we wanted to know what the velocity is r dot er plus r theta dot e theta, and we can calculate the acceleration too. So we could plot various things and figure out velocities at various times and so on. Any questions about this? Yes? Say again? Shouldn't this be what? Here? Yes. I just spelled it wrong. I spelled theta like an R like a theta, but anything else? Any questions about this question? Okay, somebody asked some question, then I'll go on. Go ahead, you got a question, I see it.
Where did the cosine h come from?
When we get equations like this, this is a constant coefficient equation because this omega is constant. Whenever you have a linear constant coefficient ordinary differential equation, it's always right to assume exponential solutions. Okay. Occasionally it's not right. if there's like some self-resonance. But 99.99% of the time, exponential solutions are the right thing. The argument of the exponential you don't know yet. You plug in the exponential. You get some kind of polynomial to solve to figure out the argument. In this case, you'll figure out that it's just omega in the exponential. It's not I omega. But minus omega also works, so we get two solutions, e to the omega t, e to the minus omega t. We take a linear combination of them. We set the initial value equal to r0. We take the derivative and set that equal to 0, and that tells us something about the difference between the two. And we take the two and we find out that the coefficient of the e to the omega t and e to the minus omega t have to be the same, and each of them has to be half of r0. And then we remember that that combination of terms is called hyperbolic cosine. That's how we do it. And we've done that so many times that we just write it down. That's how. Does that address your question? Any other questions? Yes?
Can you explain again to why the acceleration in the half direction is 0 from the line?
Yeah. Do you want me to explain it from this equation, or do you want to accept this equation and want to understand it physically? Okay, with a picture. How about computer animation? Okay. We do computer animation frame by frame. Okay, here it is. There's no force on it in this way, so it can't have an acceleration that way. But how can it be that r is getting bigger and bigger and bigger, yet there's no radial acceleration? Well, because when things are moving around, say they're moving in circles. Say this thing was just moving in circles. R is constant, yet there's a radial acceleration. So the radial acceleration has two parts to it. One part of the radial acceleration is because the velocity vector, as things go in circles, is changing from this to this, and therefore directed towards the center. And the other part of the radial acceleration is that the radius is changing. And in this problem, because there's no force in the radial direction, those two have to exactly cancel. So this has to be a motion where the centripetal term towards the center exactly cancels the radial term due to the radius increasing in time. Does that address your question? Okay. Anything else? Okay, now here's another way of looking at acceleration, which is called path coordinates. And this is not so useful as a calculation tool, but is very useful as a conceptual tool. So this is something you want to put into your intuition. How do you put it in your intuition? Maybe you should do some calculations with it, but I'm not claiming that there are very many problems where engineering-like problems where this is a helpful calculation, but it's a very helpful concept. And the thing is let's just say something is moving on some path. So this is the path of some particle. And we catch it at some time here, and we look at what's happening at this time. Now what you see is at this time, this thing has a velocity, and the velocity has to be parallel to the tangent to the path. Because remember, over here, we're looking at the position vector at one time, and we look at the position vector at a little bit later in time, and the difference between those position vectors divided by delta t is the velocity. So the velocity is tangent to the path. Okay, now I'm going to do this algebraically, but it also has a physical meaning. V is equal to my favorite equation, what I'm going to write here. V is equal to V. Now, I can multiply this by 1, and I can divide it by 1, and I can multiply it by 7 and divide it by 7, and I can multiply it by the absolute value of V and divide it by the absolute value of V. I was just wondering, how come your guys' phones never go off in the middle of class and mine always goes off in the middle of every lecture that I attend? But now I know the answer. You're not any better than I am. Okay. We can take this collection of terms and we can define it to be something we call ET, and therefore the velocity is equal to the speed times the vector in the tangent direction. Any vector is its magnitude times the unit vector in its direction. Well, if that's true, then we can take the acceleration and say the acceleration is the rate of change of velocity. But now we have this new weird formula for velocity, and we can use the product rule of differentiation, and then we get v dot et plus v et dot. But et is just a unit vector, and unit vectors can only change orthogonal to themselves. They can only change the way that er and e theta change. So the rate of change of ET has to be in the EN direction. And therefore, this has to be theta dot E n. And now what we mean by theta is this angle here, which is not the angle. Maybe I should put phi here to make it more clear. Is the angle of the velocity vector, not the angle of the polar coordinate vector. Now there's some circle which is tangent to this thing. And it's not just tangent, but it has the same curvature. So it's really spooning with this thing. But it's not spooning with its whole body. It's just spooning with its lips. And so this thing is called the osculating circle. And the word osculating means kissing. So this is a circle which is very intimate with this line. It's not just touching it, but it's tangent. It's not just tangent, but it's spooning right at that critical spot, the lips, right where they touch. Really intimate connection. So this phi dot we can associate with a angle here of this path, and therefore we can think of that as the speed divided by some radius. So then this turns into v dot times et plus v squared over rho en. Now why this is so cool is that this is the formula we had for acceleration in circular motion. And what this says is that all motion is circular motion in some sense. That is, even when we had this crazy path over here, which was an exponential spiral, at every instant in the path, we could draw a circle which doesn't just touch the path, it's not just tangent to the path, but it's intimate with the path, it's kissing the path, it's second order tangent with the path, and that circle is like this, and this particle, relative to that osculating circle, has an acceleration towards the center of the circle, which is v squared over rho, and an acceleration tangent to the circle. So at every instant in time, any particle, no matter how it's moving, you can look at its path, find the circle which is intimate with it, and its acceleration has two parts. One part along the tangent to the circle, and one part normal to the circle. And the part normal is v squared divided by the radius of the circle. Okay, any questions? Everybody happy? Goodbye.